Okay. Yeah, and first I would like to ask you if you have any questions about last week assignment.
I actually do.
Okay, go ahead.
Okay, so I was doing my simulations and I they worked, everything worked fine. And then I went into the Jupyter notebook to do like the analysis on it. And also I did the count script. And for some reason, only like four of the runs aren't executing. And I've tried to redo the run, like the simulation, like or probably like two or three times. It takes forever, so I don't do it too often. But
Mhm.
it's only not doing like four runs. So I think it's like 154. It doesn't do run 154. It doesn't do run 232 and then something else. I'm not sure why only four of them aren't working, but it goes all the way to 1,000. It's just missing those four.
Yeah, that's okay. I mean, I thought that you had only 4 runs executed, but you are saying 4 runs were not executed. That's okay.
Yeah, so like
It happens.
996 will.
Yeah, no, that's okay. This happens, and therefore I have this small script count, so that because you cannot go to the step of analysis of your Monte Carlo simulations until you are sure that you have all 1,000. Otherwise, you will get some wrong results in the analysis. So therefore, you check using this count script, and then the idea is that then you should run these few cases, like 4 cases, right? Like individually, one by one. Okay.
Okay.
And but please keep in mind that each of those cases that have not finished, say number 500, just for example, okay? Each of these cases should be run with its corresponding network, right? Network, yeah?
Mm-hmm.
Number 500, okay? Because
Mm-hmm.
remember, each of 1,000 Monte Carlo runs is supposed to have its own special network with the same number, right? Yeah. So
Mm-hmm.
in order to execute this few runs that were not completed in Monte Carlo simulations, let me just a second. Okay. Okay. Yeah. In order to run them, you should go to just your run directory where you run individual cases, right? To your run directory. Okay.
Yeah.
Then be sure that ppn physics.input has ininet equal 3, which means that your code will be using whatever network you save there, you put there, okay? Not
Mm-hmm.
it will not produce the default network because you're not interested. Okay, then you just copy network with these numbers one by one, just step by step. You take, for instance, network number 500 from directory where all 1,000 networks are, right? You copy it into your run directory, okay? You rename it to the default name, just network setup.txt, because the ppn.exec code understands only network setup.txt, not a network setup underscore 500.txt. You rename it, and then you just run this case individually, okay? Usually, from my experience, it turns out that by some reason, when you run it individually, it completes, okay? Yeah, because you don't have to tune up anything, okay? So therefore, this means that in Monte Carlo runs just some, I don't know how to call it, some interference was met during the execution. I don't know, because from my experience, when I just run them in my just individual run directory one by one, usually they executed. So therefore, then so at the end of each of these runs, additional runs, you find in your run directory the file with the final abundances, right? Yeah. And also, please check that when you run these individual cases in your run directory, that in ppn frame .input file, okay, you use the your neutron density, constant neutron density, right? And you use decay time equal 10 to the 9 years, right? Yeah. Yeah, I can show you, so I can start.
Yeah.
Okay, I have not started sharing my screen, but so far I didn't show anything. We just were talking. So now I'm going to start sharing my screen, and I will just show you. So this is my run directory here. So what I've just said, let me just repeat this. First, you check that ppn physics does have ininet equal 3. Okay, that's good. Then you check ppn frame.input that it has here the right neutron density that you were assigned to, right? Yeah, and decay time 10 to the 9. Okay, that's it. Then, okay, now where we have all this networks in what directory? Unfortunately, I don't remember that, but let me check somewhere here. Yeah, here. So this is where you're supposed to take right from my directory, I think, yeah. Yeah, here. Okay, pwd, okay. So now I go back to my run directory and I say copy from this directory, okay. Copy from there, say missing, your missing case, say network setup, whatever, 570, right? Like this, okay, it doesn't matter. 570, okay. Here, copy it in here, in my run directory, okay? Okay, so now I have this network here, network 570, but now I have to rename it to the default name network setup right here, because yeah, the code will be, so I say copy it or move it, this one to this one, okay? Okay. Now I just start execution individual for this case. So it just takes some time. This is for Jackie's neutron density, 3.1610 to the 13, right? Yeah, it doesn't matter. You just choose your own neutron density. We just wait. Okay. By the way, I think it's more instructive. Sophia, what cases, number cases were not completed? Just let's try this. Can you give me just one number?
154 was not working.
154, okay.
Yeah.
So I stop this, I will clean. Okay, now let's take 154 right here. Instead of this, 154, right? Yeah. Okay. Oops. Oh, no, not this one. The long one. Here. 154. Now this one, yeah, this one. And your neutron density, Sophia, was what's your input neutron density?
It was 3.16 times 10 to the 15th.
10 to the 15, right? 15. Okay, so let's check your case. It's interesting to check your case because I said that from my experience, usually here they complete, but if it's not, you then have maybe to tune up some parameters in PP. Let's check. I don't remember that I needed to do this. Okay, but let's see. And Jackie, did you run count script? Yeah, you have all 1000 already. Okay, good. I mean, usually this method doesn't work so well for high neutron density. And Sophie, you have 3.16 10 to the 15. Yeah, because it better works for lower. But 15 is not that high. This method is supposed to work to up to neutron densities 10 to the 18. So because but we'll see. Yeah, it takes a long time. Yeah, surprisingly long time. Yeah. It's still running. You can see here top PPNX, but that takes a long time. Yeah. So therefore this is a good example, by the way. Okay, it's finished. Let's check. Okay. Q. Okay. Okay, it says that there is some error. Initial comment. Yeah. It doesn't seem to produce any result. You're right. Okay. Yeah. There's a problem. Okay. Yeah, so first thing then we can just print output so that we see the output, input output level 1, input output level 1. Let's check. Okay. Yeah, you see this last column here, which now increasing, which is a bad sign, because this last column is actually correction to abundances, and it's supposed to be decreasing, okay? Because this method automatically stops calculation when this correction becomes small, but you can see it's increasing, and now it's the code has problems, yeah. So this is a real problem, okay? So I'm going to stop this and clean. So VPPN frame, let's check. This is because you have, higher neutron density, I think, okay. What can we change here? I think it chooses everything automatically, right? I cannot choose everything automatically. Hmm. Let me think. Okay. Okay, so I suggest that so that we don't waste our time, right? Sophia, will you please send me numbers of cases like 154 and whatever. And after our meeting, I will just check, because you see, as I said, in this code, in this program, it does everything automatically, right? So I don't have controls. Otherwise, I have to change to play with these parameters. With this one, this is just the first integration time step, dt 10 to the minus 9, the very first. This is the estimated maximum integration time. This is maximum allowed integration time step, okay? And this is the factor by which we can increase or decrease time step at each integration time step. And in this method, unfortunately, I don't have means to change them, right? Because you have executable code, but I have an access to the source code, okay? So therefore, for those specific cases that you sent me, I will change the code, right? And I will check that your cases can be run, and then I will just put this new code in your directory with slightly different name, okay? And then you can run it, okay? So otherwise we will just waste this time, and yeah, okay. So those are this all your questions? Okay, now let's continue. Because today, actually, I don't think there will be a lot of new information for you, because today I just want to explain you how you can introduce in the same calculations that you were supposed to do last week, right? How you can introduce changes of some neutron capture reaction rates, right? For instance, like in our case, Andrea constrained experimentally new constrained experimentally rates for neutron capture reactions on molybdenum 102 and molybdenum 103 isotopes, right? Which means, and I'm going to show you, I prepared this file. I showed you this file, I think the last time, probably, I don't remember. Yeah, I've just sent these two files to you by email. Have you got my email recently, like 15, half an hour ago? Yeah, okay. So this file provides neutron capture rates experimentally constrained by Andrea for molybdenum 102, okay? And as I said, we focus our preferred temperature is in billion Kelvin is 0.3, which means 300 million. So let's just focus on this temperature. And for this temperature, the second column gives the minimum experimentally constrained rate. The third column gives the maximum experimentally constrained rate, okay? So these rates, of course, they differ from NuGrid code default rates that NuGrid codes that our computation codes use. As I mentioned, I think I mentioned that NuGrid default rates for neutron capture reactions, at least, they are all taken from GINA ReaClip, right? From GINA ReaClip, okay? So therefore, the Monte Carlo runs that you did the last week, they used NuGrid default neutron capture rates, okay? And you varied them randomly, okay, within specified maximum and minimum rates. So that were determined by using a list of maximum variation factors, as we discussed last time, okay? And now the question is, what if, for instance, you want to change in your Monte Carlo calculations just one or two neutron capture reaction rates, right? In this case, molybdenum 102 and molybdenum 103 and gamma, right? Yeah. How to do this? Okay. So how to do this is explained in the file. Sorry. This is explained in the file, PDF file method multiply.pdf that can be found in the Monte Carlo directory weak iProcess impact, right? Yeah. So weak iProcess impact, this is directory where there is directory Monte Carlo runs, okay? Remember, so this is actually my Scratch outreach Pavel. iProcess, yeah, this is iProcess Sims template, but if you go to your iProcess Sims, in your iProcess Sims, there should be a directory weak iProcess impact. And inside this directory weak iProcess impact, there is a PDF file method multiply, okay? And so now here, there is a short text, actually as a reminder to myself, but of course also for students like you, which briefly explains what you should do, what changes you should make to include in your Monte Carlo simulations new rates for a number of Newton capture reactions, right? Okay. So let's just let me read this short text and show you what calculations you're supposed to do and what changes and in which files you're supposed to do. Okay, first, let the minimum and maximum experimentally constrained rates of the ice and gamma reaction are Ri min and Ri max. Okay. So this means that in the files that I sent you here, for in this case, the ice and gamma rate is molybdenum 102 and gamma, this file. The second file, will be 103 molybdenum gamma. So you go to temperature 0.3, which means 300 million Kelvin. We agreed to use this. And the second column gives me R min, minimum reaction. The third column gives me R max. Okay, so now I go back to, sorry, I don't like this thing. Do you see these screens, right? Yeah, I mean, I don't like them. Okay, yeah. I put it here. Okay, so now I take Ri min and Ri max. And first, I'm supposed to calculate a recommended rate, which is just geometric mean from mean and right, which means square root of the product of Ri min and Ri max. So, which means, here in this window, I opened just IPython calculator, right? Yeah. And first I imported NumPy package as NP. So now I have to calculate, I have to take square root NP, yeah, square root, okay, of the product. So now I just copy for 300 million 0.3 the minimum rate, right? Like this, sorry, the minimum rate. I copy it here in my Python, multiply by the maximum rate. I go here, I take the maximum rate, okay. Okay. Okay, so let me just, yeah, say R min is equal to, R min is equal to this value. So R max is equal to this value. Now R recommended, right, which was just Ri is equal NP, the square root of R min multiplied by R max, right? Yeah, like this. So this is Ri. So Ri is just geometric mean from minimum and maximum experimentally constrained rates. Okay. Now, next, first find the ratio of the recommended rate to the default that is used in NuGrid GINA Reactlib rate that is used in NuGrid codes, right? Ratio of this recommended to GINA, which means now we should go to GINA website, right? And find the rate of this same reaction for the same temperature in GINA Reactlib, because this is what is NuGrid default rate. So now I go to my website, right? And I go to GINA Reactlib. I just Google it, GINA Reactlib, okay? So now I'm here. Search rates, I can just jump to search rates. And reaction type, I need now N-gamma, I choose. And start. What's the proton number for molybdenum 42, right? 42, 102, 103, right? Search. Yeah, molybdenum, yeah. So the first reaction in molybdenum and gamma, molybdenum 1,3. So you can see the type of this reaction in this GINA base is theory, which means, of course, it's not experimentally measured yet, except Andreas results. So it's theoretical rate, which we cannot actually trust, right? And what's even worse, that it's theoretical rate that was calculated in the year 2000 using Hauser-Feshbach code non-smoker. Now we have Thales. Now we have in 2024 year. Okay, so now I click this rate, this reaction, and I click data points here, view data points, okay? And this gives me the table of GINA Reactlib or NuGrid default rates for this reaction, okay? And I find temperature 0.3, and this is this value that I need, okay? I copy it, okay? I go back to my Python notebook here, okay? And I call this rate GINA, R GINA is equal to this value, okay? This is R GINA. Now I check that what I'm supposed to do. Now I first have to find the ratio of my calculated recommended rate to GINA rate, okay? F, this is called F GINA, okay? Let me call it like this, F GINA is equal recommended, which is Ri, divided by R GINA, okay? So F GINA is this factor. And the second thing, and the last thing, now I have to calculate new maximum variation factor, right? Because experiments done by Andrea, like 3-4 years ago, they now provided a new recommended rate that we just calculated, but they also reduced the uncertainty range, right? Compared to what was from our Thales calculations. So now we have to calculate the new maximum variation factor, which should be equal to square root of the ratio of maximum rate to minimum rate. Let's call it Vmax, okay? So Vmax new is just NP square root of what R max to R min. R max divided by R min, and Vmax is equal, yeah, this one. Okay, so now I have these two numbers for the first reaction rate, molybdenum 102 and gamma, and I am going to substitute them in the right files for Monte Carlo simulations, okay? So therefore I go back to here. So first thing, okay, let's say that before you start doing your Monte Carlo simulations, right? You just wanted to see how this, okay. Okay, let's not talk about this. Let's go directly to Monte Carlo simulations. Okay, so for this, I have to go back to my Monte Carlo run directory, sorry. Monte Carlo run directory. This one as an example. Monte Carlo run, okay. Oh. A second. No, this is not right. First, I should go here. Look, because I'm going to change some rates from default to new experimentally constraints, right? Therefore, I have to also change my 1000 networks, right? Because my 1000 new networks for Monte Carlo calculations should reflect these experimental changes for a number of reactions, right? Yeah, this is the first thing that I have to do. So what I do usually then, I make a new directory. I make a new directory for networks before you used all network setup and non-context data. Now I do like this. I add here usually information about what has been changed. In this case, say molybdenum 102, right? And molybdenum 103, right? Yeah, this is what we are going to change. This is a new directory. Okay. So now I go to my old directory with these networks, and I copy from it the Fortran program. How it's called? Prepare, yeah, prepare my MC network to my new directory here. And I also copy template network setup, right? Copy template. And I also copy reaction factors. Reaction factors, okay. Reaction factors. .txt. Okay, I think that's it. So now I go to this new directory. The new directory. So with you see with this additional suffixes, molybdenum 102, molybdenum 103. So now here I have these 3 files that can be used to prepare new 1000 networks with this new data about these 2 reactions taken into account. How do I do this? If I go back to my Python notebook, here I have 2 numbers, right? Maximum variation factor, this is for molybdenum 102 so far, and this FGNA. And if I go to this method file, it says apply FGNA, what you calculated for FGNA, to the ith and gamma reaction rate in the file template network setup, and use Vmax in the file reaction factors. So this short text actually explains everything. It's very good text. I like it because it reminds me what I'm supposed to do. So, and yeah, it's very short. So now I should apply these 2 numbers, FGNA and Vmax, to 2 files in my new network setup directory. Okay. So first, let's open reaction factors. In the reaction factors, I'm supposed to apply new Vmax, maximum variation factor, only for molybdenum 102 and molybdenum 103, right? In principle, I could have more reactions with updated rates and uncertainties, right? But in this case, in your assignment, we will be changing only 2. So I search for molybdenum 102. I found it. You see, in the default setup, the maximum variation factor for molybdenum 102 and gamma was 5. And this factor 5 comes, as I explained, from those 20 Thales Hauser-Feshbach calculations, right? We have a range from 20 calculations, and the maximum rate divided by minimum is 5. Now I have reduced uncertainty. So it's Vmax now is 1.425 for molybdenum 102. So therefore I put here 1.425, right? Which means 1.43, right? I round up because you should keep the right format of numbers. Don't add extra digit, right? Yeah, so 1.43. So now let's do the similar thing for molybdenum 103, right? So this file that I sent you. Okay. Again, now I have R mean equal to 0.3 temperature. This is for molybdenum 103. So 03 minimum rate is here. R max is here. Okay, now I calculate recommended, which is Ri. Okay. Now, now I have to check. It's GINA. Okay, GINA for. Oops, sorry. GINA for now molybdenum 103 and gamma. This one. Data points table. Temperature 0.3. This is GINA for molybdenum 103. Okay, I copy it. So this is GINA. This is supposed to be GINA. Okay, this is GINA. And now I calculate FGINA. And now I calculate Vmax. So these two numbers are now for molybdenum 103 and gamma. Okay. So Vmax for molybdenum 103 1.44 rounded up. So therefore I go here. So molybdenum 103 1.44. The previous one was 4.73, larger. So your efforts, your experimental nuclear physics experiments reduced uncertainty, right? Which is very good. Okay. Now we can predict, abundances in stars with better accuracy. Okay. So 1.44, right? 1.44. Okay. So I have changed Vmax maximum variation factors for these two reactions, molybdenum 102. I save this file, and as this text explains, now I have introduced now this FGINA in template network setup. I will show you how to do this. So now I open template network setup. Okay. And I search for molybdenum 102 and 103 and gamma. Search molybdenum 103. Sorry, molybdenum 102 first, right? Okay, so this is molybdenum 102 and gamma, right? And I go to the column before the last one that contains this multiplication factors, right? That you randomly varied in your Monte Carlo simulations. So, and here I should replace 1 with FGINA, right? For molybdenum 102. So for molybdenum 102, FGINA was here. This was the first reaction. It should be 3195, right? So I should replace to 3.195, right? And I should do the similar thing for molybdenum 103, right? So this is molybdenum 103 and gamma. I should replace 1, the default multiplication factor, with this one, FG for molybdenum 3.177. 3.177. Okay, now I save this file. Okay. You see, why am I doing this? I'm doing this because first I have to shift NuGrid default rates, right, towards new experimentally constrained recommended rate. And after that, I will vary this shifted rate within reduced uncertainty, right? This just, yeah, you can think about it or you don't think about it, just follow instructions in this short file. Okay, that's it. Okay, I save this file. Okay, now don't forget to copy a template network setup into network _0. Okay. Because network setup _0 just uses default rates, okay, or in this case, default rates with changed rates for some reactions. Now I just make GFORT run. Sorry, let me first check VI this program. Yeah, we have 1000 Monte Carlo runs. Therefore, now I can compile it. GFORT run, right? I compile it. Now I have an executable A out. Now I start running it, okay? Okay, now it will run maybe a half an hour or 1 hour, but it will produce 1000 new networks for your Monte Carlo next Monte Carlo simulations, right? Yeah, in which we took into account the Andreas new experimental data on these two reactions, molybdenum 102 and molybdenum 103 and gamma, right? We could change rates, update rates of larger number of reactions, but now this is about only 2 reactions. So it will be running, but now you can see that, I mean, I've explained this for you, so you can, in your directory, try to do the same things, just, yeah, it's up to you. But in principle, after this run will finish, in your next Monte Carlo calculations, you can use these networks. So the path is similar to the previous one, except you should add these suffixes right at the end. After all data at underscore molybdenum 102 and underscore molybdenum 103. Okay, that's it. Yeah, and you should change paths to this new path in Monte Carlo run scripts. Remember, there are 2 scripts in which you have to change this path. One script that copies at the end of your Monte Carlo calculation, copies some additional necessary files. And the second more important script that runs your 1000 Monte Carlo simulations, and you just tell the script to take networks from this directory, from new directory, right? Please don't start this Monte Carlo calculations yet until this run will finish and produce 1000. I will just let you know. I will let you know in my email or whatever. I will send you an email saying that the files are prepared. I will also send you path to this directory. Okay, I think that's it. Yeah. Then otherwise, you just have to repeat what you did last week, right? Using this new path, right? Yeah. And do analysis with the same notebook, Monte Carlo notebook, with the same, but also in this notebook, Monte Carlo one zone analysis, right? You will have to change path to the directory with new varied reaction rates. This is done. Let me check where. Oh, this is done. Sorry for scrolling fast. Oh, data dir. No, that's okay, because the script that copies some additional files after the end of your Monte Carlo calculations, it will copy the right files in the right directory. So data dir, what is it? Let me just check. Yeah, data dir. Yeah, this is data dir. Okay, and of course the important thing, guys, that you will have to make a new empty directory where you will keep results of your Monte Carlo computations, new one, with changed names, of course, changed name appropriately. Add here, for instance, after low iron, add underscore molybdenum 102 and molybdenum 103. Okay, so that you will have two output Monte Carlo directories. One without changed reactions for molybdenum, the other with changed. Okay, that's it actually for today. That's it. And so the last thing, Sophia, please send me the numbers of cases. And if you don't mind, Sophia, when I test the code and make a new executable, if you don't mind, I will go to your directory and try to run, right? Just maybe one case. Then I will let you know by email that you can go there and repeat them, okay?
I'm still running the simulations. I started it earlier, and it's got like 100 left, so I'll send them when you're done.
Okay, yeah, sure, no problem. So let me just now send me email saying that all calculations are done and these cases have not been completed, numbers, okay, numbers, whatever. Okay, then I'm going to stop sharing my screen first and stop video recording if you have no questions. So this is actually for next week, like not necessarily a week, maybe 2 weeks, because yeah, important thing. Next week I will leave on Monday actually, right? And because I will be going to Europe next week, I will probably have jet lag, so let's not meet. And but after that, at least until like August 25th, you can communicate with me via my email if you have any questions or find any bugs. So I will respond to your emails until August 25th. Okay. After that, I will have 2 weeks of true summer vacation. Okay. But until August 25th, and from the end of next week, I will be available to answer your questions. Okay. Yeah, this is also important information for you as well as for Tristan and Andrea. I mean, it's important for me, but yeah. Okay, then I'm going to stop sharing, to stop video recording. Okay.